Hello there and welcome to the Deep Sleep Discoveries channel. I'm so glad you've joined me tonight. Tonight's journey takes us through 100 quiet truths about stars, those distant suns that fill our skies with light and our universe with possibility. Some facts will carry you through stellar births in vast nebulae. Others will guide you past dying giants and spinning remnants. Each one is a small window into the cosmos, a gentle reminder that we are connected to something far larger than ourselves. If you enjoy these peaceful explorations, consider liking and subscribing or sharing your thoughts in the comments. But for now, you don't need to do anything at all. Just settle into comfort, let your breathing slow, and allow your thoughts to drift among the stars. A star is not solid like a planet, nor is it simply gas floating in space. It exists in a fourth state of matter called plasma, where atoms are stripped of their electrons and charged particles swirl in organized chaos. Gravity pulls all of this inward with immense force, compressing the plasma until temperatures soar into the millions of degrees. This compression is so powerful that it ignites nuclear fusion at the star's core, transforming it from a collapsing cloud into a glowing sphere of light. The balance between gravity's inward crush and fusion's outward push creates stability, allowing stars to shine steadily for billions of years. Without gravity, there would be no stars, no fusion, no light. Everything we see in the night sky exists because gravity learned to hold fire in its hands. And within that delicate balance, entire worlds find their warmth. If you could line up 109 Earths side by side, they would stretch across the sun's diameter. It's a staggering comparison, one that reminds us how small our world truly is against the scale of even an ordinary star. Yet the sun is not particularly large by cosmic standards. It sits comfortably in the middle range, neither a giant nor a dwarf, but something perfectly suited to nurturing life on nearby planets. Its width measures about 1.4 million kilometers, a distance light itself takes nearly 5 seconds to cross. From our vantage point on Earth, the sun appears as a modest disk in the sky, no larger than the moon to our eyes. But that's only an illusion of distance. Up close, the sun is an overwhelming presence, vast enough to contain over 1 million Earths within its volume. To imagine standing on its surface is to confront scale that defies human intuition. And yet, this immense sphere is our closest star, the one we know most intimately. At the heart of every star, conditions become so extreme that atomic nuclei overcome their natural repulsion and merge together. This process, called nuclear fusion, releases tremendous amounts of energy in the form of light and heat. For most stars, hydrogen atoms fuse into helium, the simplest and most efficient reaction. Each fusion event converts a tiny amount of mass directly into energy, following Einstein's famous equation. Though each individual reaction releases only a small amount, the sheer number of fusions happening every second creates an outpouring of power that can shine across billions of kilometers. This energy radiates outward from the core, taking hundreds of thousands of years to work its way through the star's dense layers before finally escaping into space as light. Without fusion, stars would collapse under their own gravity in moments. Fusion is both the heartbeat and the defiance of a star, the process that transforms simple hydrogen into the brilliance we see above. And it all happens in the crushing darkness at a star's center, hidden from view. When you look at the stars, you might notice that they don't all shine with the same hue. Some glow white, others pale blue, still others deep orange or red. These colors are not decorative but diagnostic, direct indicators of how hot a star's surface burns. The relationship is straightforward. The hotter the star, the bluer its light. Cooler stars emit light that shifts toward the red end of the spectrum. This connection between temperature and color is governed by the physics of blackbody radiation, the same principle that makes heated metal glow first red, then orange, then white as it gets hotter. Astronomers use this relationship to measure stellar temperatures from across the galaxy, reading a star's heat in the colors it broadcasts into space. A star's color can tell you not only its temperature, but also hints about its age, mass, and stage of life. The night sky is painted in thermal gradients, each star a visible thermometer glowing with its own signature hue. To see color in starlight is to witness temperature made luminous. Among the stars, blue giants reign as the hottest, their surfaces blazing at temperatures exceeding 30,000 degrees Celsius. These stars burn with such intensity that most of their light spills into the ultraviolet range, invisible to human eyes, but devastating to anything nearby. At the opposite end of the spectrum, red dwarfs and red giants glow at comparatively modest temperatures, often around 3,000 degrees or less. Though still unimaginably hot by earthly standards, they are cool enough that their light peaks in longer, redder wavelengths. Between these extremes lie stars of every temperature, from orange K-types to yellow G-types like our Sun to white A-types. Each color represents a different balance of fusion and mass, a different stage in the stellar story. Blue stars live fast and die young, burning through their fuel in mere millions of years. Red stars, particularly red dwarfs, can endure for trillions. The color of a star is a window into its fate, a preview written in light of how its story will unfold. When you watch a star on a clear night, it often appears to twinkle, flashing brighter and dimmer in rapid succession. This flickering is not caused by anything happening at the star itself, but by turbulence in Earth's atmosphere. As starlight travels through layers of moving air with varying temperatures and densities, it bends and shifts, making the star appear to dance. Planets, by contrast, twinkle less noticeably because they show a small disk rather than a single point of light, averaging out the atmospheric distortion. Astronomers call this effect atmospheric seeing, and it's one reason why telescopes are placed on mountaintops or in space, to escape the blurring effects of our air. In the vacuum of space, stars shine with perfect steadiness, their light unwavering across the cosmic void. The twinkling we see is a reminder that we observe the universe through a veil, our atmosphere both protecting us and obscuring the clarity of distant light. Even the clearest night sky is filled with motion we cannot see directly. Deep within the sun, far from the warm light we feel on our skin, lies a furnace of unimaginable heat. The core temperature reaches approximately 15 million degrees Celsius, hot enough to strip atoms bare and force hydrogen nuclei together in fusion. At these temperatures, matter behaves in ways completely alien to everyday experience. Particles move at tremendous speeds, colliding with such force that nuclear barriers break down. The pressure is equally extreme, about 250 billion times Earth's atmospheric pressure, compressing the core into a density far greater than lead. In this hellish environment, roughly 600 million tons of hydrogen fuse into helium every second, releasing the energy that eventually becomes sunlight. Yet that energy doesn't escape quickly. Photons born in the core scatter and bounce through the sun's dense interior for tens of thousands of years before finally reaching the surface. By the time sunlight touches your face, it has travelled an incredible journey from the heart of a stellar inferno. The warmth you feel is ancient, born in conditions no human technology can replicate. The Sun sits approximately 150 million kilometres from Earth, a distance astronomers call 1 astronomical unit. Light, travelling at 300,000 kilometres per second, still needs over 8 minutes to cross that vast gulf. This means that when you look at the Sun, you are seeing it as it was slightly more than 8 minutes ago, not as it is in this exact moment. If the Sun were to suddenly vanish, we would continue to see it shining in the sky for those final 8 minutes before darkness arrived. The same principle applies to everything we see in space. The farther away an object is, the further back in time we are looking. Starlight reaching us tonight may have left its source decades, centuries, or even millennia ago. In this way, the night sky is a time machine, showing us the universe not as it is, but as it was. Even our closest star, the one that lights our days, exists for us only in the recent past. The present moment of the Sun is always just beyond our reach. When stars form from collapsing clouds of gas, they inherit the chemical composition of the early universe, which is overwhelmingly simple. Hydrogen, the lightest and most abundant element, makes up about 73% of a typical star's mass. Helium accounts for another 25%, leaving only about 2% for all other elements combined. Astronomers call everything heavier than helium metals, a term that includes carbon, oxygen, iron, and beyond. This metal content varies between stars. Ancient stars formed when the universe was young contain almost no heavy elements, while newer stars like our Sun carry the enriched material scattered by generations of supernovae. The Sun's composition reflects billions of years of cosmic recycling, but even so, it remains predominantly hydrogen and helium. These two simple elements are the building blocks of starlight, the fuel that powers fusion and creates the brilliance we see scattered across the heavens. Everything else, all the complexity of chemistry and life, is a trace impurity in an ocean of primordial gas. Every second, deep in the Sun's core, approximately 600 million tons of hydrogen undergo fusion, transforming into helium. Of that mass, about 4 million tons are converted directly into energy according to Einstein's equation, radiating outward as light and heat. It sounds like an enormous loss, and it is, yet the Sun contains enough hydrogen to continue this process for another 5 billion years without exhausting itself. The energy released by this continuous fusion is what keeps the Sun shining, what warms our planet, what drives our weather, and supports all life on Earth. To put the scale in perspective, in just 1 second, the Sun releases more energy than humanity has used throughout its entire history. That energy spreads outward in all directions, and Earth intercepts only a tiny fraction, about 1/2 of the total output. Yet even that sliver is enough to power our entire biosphere. The Sun's generosity is almost incomprehensible. A fusion engine running day and night, converting matter into light with perfect reliability. A star exists in a state of constant tension, a battle between two fundamental forces. Gravity pulls all of the star's mass inward, trying to collapse it into the smallest possible space. Nuclear fusion in the core pushes outward, generating heat and pressure that resist gravity's crush. When these two forces balance perfectly, the star achieves what astronomers call hydrostatic equilibrium, a stable state that can last for billions of years. If fusion weakens, gravity gains the upper hand and the star contracts, heating the core until fusion intensifies again. If fusion becomes too vigorous, the star expands, cooling slightly until balance returns. This self-regulating mechanism allows stars to maintain remarkably steady output over cosmic timescales. Our Sun has been in equilibrium for 4.6 billion years and will remain so for billions more. But equilibrium is not eternal. When a star exhausts its fuel, fusion falters and gravity wins, collapsing the core and transforming the star into something new. Every star's life is a temporary truce between collapse and explosion. From the moment a star is born, its mass shapes everything that follows. Mass determines how hot the core becomes, how quickly fusion proceeds, what elements can be forged, and ultimately, how the star will die. Low-mass stars burn their fuel slowly and can live for trillions of years, eventually fading into white dwarfs. Medium-mass stars like our Sun shine for billions of years before swelling into red giants and gently shedding their outer layers. Massive stars, anything above 8 solar masses, live fast and furious, exhausting their fuel in mere millions of years before exploding as supernovae. The most massive stars might collapse directly into black holes, while slightly smaller ones leave behind neutron stars. There is no escaping this relationship. A star cannot choose a different path or extend its life through effort. Its fate is written in its mass from the very beginning, an inevitable trajectory carved by the laws of physics. To know a star's mass is to know its destiny. The lifespan of a star varies enormously depending on its mass. The most massive stars, burning with ferocious intensity, may live only 10 to 20 million years before exploding. Medium-sized stars like our Sun enjoy lifespans of about 10 billion years. But the smallest stars, red dwarfs with just a fraction of the Sun's mass, can shine for 10 trillion years or more, thousands of times longer than the current age of the universe. This inverse relationship between mass and lifespan seems counterintuitive at first. Shouldn't a bigger star with more fuel last longer? But massive stars burn so hot that they consume their hydrogen at vastly accelerated rates, racing through their fuel reserves. Small stars, cooler and more efficient, sip their hydrogen carefully, stretching their supply across unimaginable ages. The universe is currently only 13.8 billion years old, which means not a single red dwarf has yet reached old age. Every red dwarf ever born still shines, and will continue shining long after stars like our Sun have faded into darkness. Our Sun ignited about 4.6 billion years ago, condensing from a cloud of gas and dust left behind by earlier generations of stars. We know its age with remarkable precision by studying meteorites, ancient rocks that formed alongside the Sun and have remained largely unchanged since. The Sun has spent these billions of years in a stable phase called the main sequence, steadily fusing hydrogen into helium at its core. It has already lived through roughly half of its expected lifetime. In another 5 billion years, it will exhaust the hydrogen in its core and begin transforming into a red giant, swelling to engulf the inner planets. But for now, the Sun remains in its prime, middle-aged by stellar standards, providing the same steady warmth it has offered for eons. Life on Earth has existed for most of the Sun's lifetime, evolving under the same star that shines today. When you feel sunlight on your skin, you are touching energy from a star that has been burning since long before continents formed, before complex life emerged, before anything resembling us walked the Earth. Stars are not born from nothing. They emerge from vast clouds of gas and dust known as nebulae, molecular clouds that can span hundreds of light years and contain enough material to birth thousands of suns. Within these clouds, gravity slowly pulls material into denser clumps. As a clump grows, its gravitational pull strengthens, drawing in more gas and dust in a runaway process. The collapsing material heats up from compression, and at the center, a protostar begins to form. Over hundreds of thousands of years, the protostar gathers mass and temperature until conditions at its core reach the threshold for nuclear fusion. At that moment, the protostar ignites, becoming a true star, and the powerful radiation and stellar winds it produces begin to clear away the surrounding gas. What remains is a newborn star, often surrounded by a disk of leftover material that may one day form planets. Nebulae are the wombs of the cosmos, the places where starlight begins its long journey. To see a nebula glowing in telescope images is to witness creation itself, the raw ingredients of the universe assembling into something radiant. Astronomers organize stars into 7 main spectral classes based on their surface temperature and the light they emit. From hottest to coolest, these classes are O, B, A, F, G, K, and M, often remembered by the mnemonic, "Oh, be a fine girl, guy, kiss me." O-type stars burn blue-white at over 30,000 degrees Celsius, while M-type red dwarfs glow at a mere 2,500 degrees. Each class is further subdivided with numbers from 0 to 9, with 0 being the hottest within that class. The Sun, for example, is classified as G2, placing it in the middle of the G-type range. This classification system, developed in the early 20th century, allows astronomers to quickly understand a star's properties just from its spectral type. Temperature, color, size, luminosity, and even expected lifespan are all encoded in those simple letters and numbers. The system has been refined over the decades to include additional classes for extremely cool objects like brown dwarfs, L, T, and Y types. Stellar classification is one of astronomy's most elegant tools, organizing the immense diversity of stars into a comprehensible pattern. The Sun belongs to spectral class G2V, which places it among the stars we call yellow dwarfs. The term yellow dwarf is somewhat misleading, however. If you could observe the Sun from space, you would see that it actually emits white light, a balanced mixture of all visible wavelengths. The Sun only appears yellow when viewed from Earth because our atmosphere scatters shorter blue and violet wavelengths more efficiently than longer red and yellow ones, leaving a yellowish tint for surface observers. In space, without atmospheric interference, the Sun would look distinctly white to your eyes. Despite the dwarf label, the Sun is neither particularly small nor particularly large. It's a main sequence star, meaning it's in the stable phase of its life, steadily fusing hydrogen into helium. About 90% of all stars spend most of their lives on the main sequence, and among those, the Sun sits comfortably in the middle range, neither a massive giant nor a tiny red dwarf. It's this average nature that makes the Sun so reliable, providing billions of years of steady energy for planets that orbit nearby. Though they are faint and nearly invisible to the naked eye, red dwarfs dominate the stellar population of the galaxy. These small, cool stars, classified as M-type, comprise roughly 3/4 of all stars in the Milky Way and likely in the universe as a whole. Their low mass, typically between 7.5% and 50% that of the Sun, means they burn hydrogen slowly and inefficiently, glowing with a dim red light. Despite their abundance, not a single red dwarf is visible to the unaided eye from Earth. The nearest one, Proxima Centauri, requires a telescope to observe despite being only 4.2 light-years away. This invisibility has long biased our understanding of the universe. When we look at the night sky, we see primarily the rare, massive, luminous stars, the cosmic outliers. The true population of the galaxy is far quieter, a sea of small red suns shining steadily in the background, unnoticed but essential to the galaxy's structure. They are the universe's hidden majority, outnumbering all other types of stars combined. The smallest red dwarfs possess such frugal energy budgets that they can shine for 10 trillion years, perhaps even longer. To put that in perspective, the universe itself is only 13.8 billion years old, less than 1/500th the potential lifespan of a red dwarf. These stars burn their hydrogen so slowly and mix their material so thoroughly that they can access nearly all of their fuel, not just the core material like larger stars. This extreme longevity means that every red dwarf ever born still exists today, shining exactly as it did billions of years ago. None have yet reached old age or faded into white dwarfs. In the far future, when stars like our Sun have long since exhausted themselves and massive stars are distant memories, red dwarfs will continue to glow. They will be the last lights in a darkening universe, burning faithfully through eras we can scarcely imagine. Their patience is almost infinite, outlasting galaxies, outlasting the formation of new stars, witnesses to the long twilight of cosmic time. At the opposite extreme from red dwarfs are blue giants, massive stars that burn with such ferocity that they exhaust their hydrogen fuel in mere millions of years. These stars can be dozens of times more massive than the Sun, and their cores reach temperatures where fusion proceeds at an explosive rate. The luminosity of a blue giant can exceed 100,000 times that of the Sun, pouring energy into space at a staggering pace. This brilliance comes at a cost. The star consumes its hydrogen reserve so quickly that its lifetime is compressed into a cosmic instant. A blue giant born at the time of the dinosaurs would likely have already exploded by now. Their rarity in the galaxy is partly due to this brief existence. Though many may form, they vanish quickly, leaving behind neutron stars or black holes. These stars are the fireworks of the universe, spectacular but fleeting, burning out while smaller stars are just settling into their long, slow lives. Their light is a glimpse of extreme physics, a reminder that the universe contains engines far more powerful than we can easily comprehend. When a star like the Sun exhausts its hydrogen fuel, it swells briefly into a red giant before shedding its outer layers into space. What remains is the exposed core, compressed into an object about the size of Earth but containing a significant fraction of the original star's mass. This remnant is called a white dwarf, a dense, hot sphere that no longer generates energy through fusion. White dwarfs shine only with leftover thermal energy, glowing white-hot at first but gradually cooling over billions of years. With no fusion to support them against gravity, white dwarfs are held up by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain point. This gives white dwarfs a strange property. The more massive they are, the smaller they become, the opposite of normal stars. The outer layers have been stripped away, leaving only the crystalline heart of what was once a living sun. These stellar corpses drift through the galaxy, monuments to the inevitability of stellar death. The density of a white dwarf defies everyday intuition. With roughly the mass of the Sun compressed into a sphere the size of Earth, the material inside is packed incredibly tightly. A single teaspoon of white dwarf matter would weigh approximately 5 tons, about the weight of an elephant. This extreme density results from gravitational compression that has squeezed atoms as close together as quantum mechanics allows. In a white dwarf, atoms are not intact as they are in ordinary matter. Electrons are stripped away and exist in a degenerate state, forming a kind of quantum gas that resists further compression. The atomic nuclei are pressed together in a crystalline lattice, a structure more like a metal than anything we encounter in daily life. If you could somehow bring a piece of a white dwarf to Earth, it would be unimaginably heavy, impossibly hot, and would immediately explode from the sudden release of pressure. These objects represent matter in an extreme state, one step removed from the even stranger physics of neutron stars. When a massive star explodes as a supernova, its core may collapse into something even denser than a white dwarf, a neutron star. These objects are typically only about 20 kilometers in diameter, small enough to fit within a large city, yet they contain 1.4 to 2 times the mass of the Sun. The collapse is so extreme that protons and electrons are forced together, merging into neutrons and creating matter at densities found nowhere else outside black holes. A neutron star is essentially a giant atomic nucleus, held together by gravity and neutron degeneracy pressure. Their surfaces are smooth and incredibly hard, covered by a thin crust of iron atoms crushed into crystalline structures. Below that lies a neutron fluid, and at the very core, matter may exist in exotic states that physics is only beginning to understand. Neutron stars spin rapidly, often hundreds of times per second, and possess magnetic fields trillions of times stronger than Earth's. They are among the strangest objects in the universe, laboratories of extreme physics that push matter to its absolute limits. If white dwarfs represent extreme density, neutron stars take that concept to an almost unimaginable level. A single teaspoon of neutron star material would weigh approximately 1 billion tons, roughly the mass of Mount Everest compressed into something you could hold in your hand. At this density, matter is packed so tightly that a neutron star's gravity warps space-time noticeably around it, bending the paths of light and causing relativistic effects. The surface gravity is about 200 billion times stronger than Earth's, which means that if you could somehow stand on a neutron star, you would be instantly flattened into a layer of atoms just 1 atom thick. Mountains on a neutron star, if they exist, would be only millimeters high, crushed down by the overwhelming pull of gravity. These objects represent the densest stable matter we know of. Beyond this point, not even neutrons can resist gravity's crush, and the object collapses further into a black hole. Neutron stars sit at the very edge of what matter can withstand before crossing into the abyss. Not every collapsing cloud of gas becomes a true star. If the mass is too low, the core never reaches the temperature and pressure needed to ignite hydrogen fusion. These objects, called brown dwarfs, occupy a twilight zone between the largest planets and the smallest stars. They typically range from about 13 to 80 times the mass of Jupiter, large enough to fuse deuterium, a heavy form of hydrogen, briefly in their youth, but not massive enough to sustain the proton-proton chain that powers true stars. Brown dwarfs glow faintly from leftover heat from their formation and from deuterium burning, but they gradually cool and dim over time. They emit most of their light in the infrared, making them difficult to detect. Despite being called failed stars, brown dwarfs are fascinating objects in their own right, with atmospheres that can contain clouds of molten iron or silicates. They blur the boundary between stellar and planetary physics, challenging our definitions and revealing that the universe creates objects across a continuous spectrum of masses. Before a star ignites fusion and joins the main sequence, it exists as a protostar, a dense core of gas still gathering mass from its surrounding cloud. Protostars can't yet be called true stars because their cores haven't reached the temperatures needed for sustained hydrogen fusion. Instead, they glow from gravitational energy, heating up as material falls inward and compresses. This phase can last hundreds of thousands of years for a Sun-like star, or even longer for smaller ones. During this time, the protostar is often hidden deep within a cocoon of dust, invisible in optical light but glowing brightly in infrared. Powerful jets of material stream from the protostar's poles, carrying away excess angular momentum and carving cavities in the surrounding cloud. These jets can stretch for light years, marking the protostar's location even when the star itself cannot be seen. The protostellar phase is a period of chaos and growth, a transformation from diffuse cloud to concentrated fusion engine. Only when the core finally ignites does the protostar earn its place among the stars. Not all stars shine with constant light. Variable stars brighten and dim in regular cycles, driven by internal processes that cause them to physically expand and contract. As a star's outer layers swell, its surface cools and dims. As they contract, the surface heats and brightens. These pulsations can occur over periods ranging from hours to months, creating rhythmic changes in luminosity that astronomers can measure with precision. Some variables, like Cepheids, pulse with such regularity that they function as cosmic clocks. Others, like mirror variables, undergo slower, more dramatic changes, sometimes varying by factors of 100 or more. Eclipsing binaries, where two stars orbit each other, also appear variable as one star passes in front of the other from our perspective. Variable stars have been crucial to astronomy, allowing scientists to measure distances across the universe and understand stellar structure in ways that steady stars cannot reveal. Their changing light carries information about the star's interior, making them natural laboratories for testing theories of stellar physics. Among variable stars, Cepheids hold a special place in astronomy. These yellow supergiants pulsate with remarkable regularity, expanding and contracting over periods ranging from days to months. What makes them invaluable is a direct relationship discovered in 1912 by Henrietta Leavitt. The longer a Cepheid's pulsation period, the more luminous it is intrinsically. This period luminosity relationship allows astronomers to determine a Cepheid's true brightness just by timing its pulsations. By comparing that true brightness to how bright it appears from Earth, they can calculate its distance with impressive accuracy. Cepheids became the first standard candles, reliable distance markers that opened up the universe to measurement. Edwin Hubble used Cepheids in the Andromeda galaxy to prove that it lay far beyond the Milky Way, demonstrating that the universe contained countless galaxies. Today, Cepheids remain essential for calibrating the cosmic distance ladder. Their steady, predictable pulsing hearts beat out measurements across millions of light years, turning the universe from an unknowable expanse into something we can map and measure. Our Sun travels through space alone, unaccompanied by any stellar companions. This solitary state is actually less common than we once thought. Current estimates suggest that at least half of all Sun-like stars exist in binary systems, where two stars orbit a common center of mass. Many stars are part of even more complex systems, with 3, 4 or more stars bound together in intricate gravitational dances. These multiple star systems can be quite stable, with stars orbiting in hierarchical arrangements where close pairs orbit each other while more distant companions circle them both. For planets in such systems, the sky can be a complex tapestry of suns rising and setting at different times, creating seasons and light cycles utterly unlike anything on Earth. Binary systems are particularly important for astronomy because they allow direct measurements of stellar masses using Kepler's laws. The way two stars orbit reveals their masses with precision impossible for solitary stars. These stellar partnerships remind us that the universe favors companionship over isolation. Binary stars are pairs of stars gravitationally bound to each other, orbiting around their common center of mass like cosmic dance partners. Depending on the survey and the methods used, astronomers estimate that between 40% and 60% of Sun-like stars exist in binary or multiple systems. This high percentage suggests that binary formation may be a natural outcome of the star formation process. When a cloud of gas collapses, it often fragments or retains enough angular momentum that two distinct cores form instead of one. The separation between binary stars varies enormously. Some are so close they nearly touch, completing orbits in hours. Others are separated by thousands of astronomical units, taking millennia to complete a single orbit. Close binaries can interact dramatically, with one star stripping material from its companion or both stars eventually merging. Wide binaries behave more like independent stars that happen to share a slow, distant dance. Understanding binary stars is crucial because they shape so much of galactic evolution, from supernova rates to the formation of exotic objects like neutron stars and black holes. Among the giants of the cosmos, Scuti stands as one of the largest stars ever discovered. This red supergiant, located about 9,500 light-years away in the constellation Scutum, has a radius estimated at roughly 1,700 times that of the Sun. Measuring such enormous stars is challenging because their outer atmospheres are diffuse and poorly defined, making the exact edge of the star difficult to determine. Still, by any measure, Scuti is almost incomprehensibly vast. Its sheer scale defies intuitive understanding. If you could travel at the speed of light around Scuti's equator, the journey would take about 7 hours. For comparison, circling the Sun at light speed takes only 14.5 seconds. Despite its size, Scuti is relatively cool for a star, with a surface temperature around 3,300 degrees Celsius, which gives it a deep red color. These hypergiant stars are incredibly rare and unstable, losing mass through powerful stellar winds. Scuti won't remain this large forever. It's nearing the end of its life and will likely explode as a supernova within the next few million years. To truly grasp the scale of Scuti, imagine placing it at the center of our solar system where the Sun currently resides. Its outer atmosphere would engulf Mercury, Venus, Earth, and Mars entirely. It would stretch beyond the asteroid belt and reach well past the orbit of Jupiter, possibly even extending towards Saturn. The inner planets wouldn't just be close to this star, they would be inside it, vaporized within its tenuous but still extremely hot outer layers. Standing on Jupiter's clouds, if Jupiter could somehow survive, Scuti would fill more than half the sky, a vast red wall of glowing gas dominating the heavens. The amount of material contained in such a star is staggering, despite the fact that its density is actually quite low. The outer regions of hypergiants are so diffuse that they're nearly a vacuum by Earth standards, yet they still shine because of their sheer volume. These cosmic behemoths show us that size in the universe operates on scales that challenge human comprehension. At the bottom end of the stellar mass range sit the smallest true stars, red dwarfs with masses as low as about 7.5% that of the Sun. Below this threshold, objects don't have enough gravitational pressure to ignite sustained hydrogen fusion, and they become brown dwarfs instead. These minimum mass stars are tiny by stellar standards, with radii only slightly larger than Jupiter, though they're far denser. Despite their small size, they are true stars, fusing hydrogen in their cores and shining with their own light, however faint. Their surface temperatures hover around 2,500 degrees Celsius, cool enough that they glow deep red. Their luminosity can be less than 1/10,000th that of the Sun, making them nearly invisible even at relatively close distances. Yet these tiny stars have staying power. Because they burn their fuel so slowly, they can shine for trillions of years. The smallest stars are the universe's endurance champions, outlasting their larger, brighter cousins by factors of thousands. They are proof that in stellar terms, small and dim can mean incredibly long-lived. Betelgeuse, the bright red star marking Orion's shoulder, is a red supergiant approximately 700 times the diameter of the Sun. If placed at the center of our solar system, Betelgeuse would extend well beyond the orbit of Mars, swallowing the 4 inner planets entirely. The exact size of Betelgeuse is difficult to pin down because it's a variable star that pulses and changes size over time, and its outer atmosphere is not sharply defined. Recent measurements suggest its radius varies between about 600 and 800 solar radii. Despite its enormous size, Betelgeuse is relatively close to us in cosmic terms, lying only about 550 light-years away. This proximity, combined with its size and brightness, makes it one of the few stars whose surface can be directly imaged by modern telescopes, revealing details of its turbulent, convecting atmosphere. Betelgeuse is nearing the end of its life and could explode as a supernova at any time within the next 100,000 years, perhaps even tomorrow. When it does, it will briefly outshine every other star in the night sky. At the upper extreme of stellar mass lie the true giants, stars exceeding 100 solar masses. These behemoths are extraordinarily rare because they push against several physical limits. As stars become more massive, their radiation pressure becomes so intense that it can blow away infalling material, limiting how large they can grow. Stars above about 150 solar masses may be theoretically unstable, unable to hold themselves together against their own luminosity. Yet a few examples exist, like R13601 in the Large Magellanic Cloud, which weighs in at around 260 solar masses. These ultramassive stars burn with ferocious intensity, their cores reaching temperatures where fusion can produce elements all the way up the periodic table. Their lifetimes are fleeting, measured in millions of years rather than billions, and they end in the most violent supernova known, sometimes called hypernovae. Some may even collapse directly into black holes without exploding at all. These stellar titans shape their galaxies with powerful winds and radiation, but they are ghosts, gone almost as soon as they appear. In the heart of the Tarantula Nebula within the Large Magellanic Cloud lies R136A1, the most massive star currently known. With an estimated mass of around 260 times that of the Sun, it pushes the theoretical limits of how massive a star can become. When it first formed, it may have been even heavier, possibly exceeding 300 solar masses, but intense stellar winds have already blown away significant portions of its outer layers. R13601 is also extraordinarily luminous, shining with the power of nearly 9 million suns. Its surface temperature exceeds 50,000 degrees Celsius, making it glow an intense blue-white. Despite its incredible mass and brightness, R13601 is not the largest star by volume. Massive stars remain relatively compact because their fierce radiation and high temperature keep them from swelling like cooler giants. R13601 will burn through its fuel quickly, perhaps living only a few million years before ending in a catastrophic supernova or collapsing into a black hole. It represents the extreme upper limit of what stars can be. Eta Carinae is one of the most luminous and unstable stars known in our galaxy. This massive binary system, located about 7,500 light-years away, emits roughly 5 million times more energy than the Sun, most of it in ultraviolet wavelengths invisible to our eyes. The primary star is estimated to be between 100 and 150 solar masses, making it one of the most massive stars in the Milky Way. What makes Eta Carinae particularly fascinating is its violent history. In the 1840s, it underwent a massive eruption known as the Great Eruption, briefly becoming the second brightest star in the night sky despite its vast distance. This outburst ejected more than 10 solar masses of material, creating the beautiful homunculus nebula that now surrounds the star. Eta Carinae remains unstable, and astronomers believe it could explode as a supernova at any time. When it does, it may be visible during daylight and could temporarily outshine the full moon. It is a star living on borrowed time, spectacular and doomed. While massive stars blaze with the light of millions of suns, the faintest stars are almost invisible even when relatively nearby. The dimmest red dwarfs emit less than 1/10,000th of the Sun's luminosity, making them extraordinarily difficult to detect. Proxima Centauri, the nearest star to our solar system at just 4.2 light-years away, is one of these faint red dwarfs. Despite being our closest stellar neighbour, it's completely invisible to the naked eye, requiring a telescope to observe. If Proxima Centauri replaced the Sun, Earth would be plunged into a dim, reddish twilight, receiving far too little energy to maintain liquid water. Yet these faint stars dominate the galaxy numerically, making up the vast majority of stellar population. Their dimness has long hidden them from casual observation, leading to an incomplete picture of the universe. Only with modern infrared telescopes have astronomers begun to fully appreciate how common these whisper-quiet stars truly are. They are the universe's background radiation, too faint to notice individually but collectively forming the foundation of galactic structure. Among neutron stars, magnetars represent the most magnetically extreme objects known. Their magnetic fields can reach strengths of 100 billion to 1 quadrillion times that of Earth, so powerful that they distort the very atoms around them. At these intensities, the magnetic field becomes a dominant force capable of warping the shape of atoms and influencing the quantum vacuum itself. If a magnetar passed within halfway to the Moon, its magnetic field would be strong enough to erase every credit card on Earth and potentially disrupt the bioelectrical systems in our bodies. When a magnetar's crust shifts suddenly, often just by millimeters, it releases a starquake that reorganizes the magnetic field and produces a giant flare. These flares release more energy in 1/10 of a second than the Sun emits in 100,000 years. Fortunately, magnetars are rare, with only about 30 known in our galaxy, and none are close enough to pose any threat to Earth. They are natural laboratories for studying physics in conditions impossible to recreate anywhere else in the universe. Pulsars are rapidly rotating neutron stars that emit beams of radiation from their magnetic poles. As the star spins, these beams sweep across space like a lighthouse, and if Earth happens to lie in the path of the beam, we detect a pulse of radio waves or light. The fastest pulsars, called millisecond pulsars, can rotate more than 700 times per second. At these speeds, a point on the star's equator is moving at a significant fraction of the speed of light, roughly 15% to 20% for the fastest ones. The regularity of pulsar pulses is extraordinary. Some pulsars keep time with a precision that rivals atomic clocks, drifting by only fractions of a second over years. This stability makes them useful for tests of general relativity and even for navigation. NASA has proposed using pulsars as natural GPS beacons for deep space navigation. These spinning stellar remnants are cosmic timekeepers, their relentless rotation marking the passage of seconds with mechanical precision. They are among the most reliable periodic phenomena in the universe. The record for the fastest spinning pulsar belongs to PSRJ 1748-2446 AD, which rotates an astonishing 716 times per second. At this speed, a point on its equator travels at approximately 24% the speed of light. This is close to the theoretical maximum rotation rate for a neutron star. Spin it much faster, and centrifugal forces would overcome gravity and tear the star apart. PSRJ 1748-2446 AD is a millisecond pulsar, likely spun up to these extreme speeds by stealing matter from a companion star. As material from the companion spiraled onto the neutron star, it transferred angular momentum, spinning the pulsar faster and faster over millions of years. The process is called recycling because it takes an old, slowly rotating neutron star and spins it back up to youth-like speeds. The precision of this pulsar's rotation is remarkable. Each rotation takes only 1.396 milliseconds, and this period changes by less than a trillionth of a second per year. To observe such an object is to glimpse matter at the absolute limit of what physics allows. Stars are not always perfect spheres. When a star rotates rapidly, centrifugal force pushes material outward at the equator, causing the star to bulge and flatten slightly at the poles. This distortion creates an oblate shape, like a sphere that's been gently compressed from top and bottom. One of the most extreme examples is Achernar, a bright blue star in the constellation Eridanus. Achernar spins so rapidly that its equatorial diameter is approximately 50% larger than its polar diameter, making it visibly flattened. This rapid rotation affects the star's surface temperature and brightness, with the poles being hotter and brighter than the equator due to a phenomenon called gravity darkening. Other fast-rotating stars like Altair and Vega also show measurable oblateness, though not as extreme. These distorted stars challenge the simple picture of stars as round, uniform spheres. They remind us that rotation is a powerful force, capable of reshaping even something as massive as a sun, warping their light and structure in ways that reveal the dynamic nature of stellar physics. Achernar, the ninth brightest star in the night sky, holds the distinction of being one of the flattest stars known. This blue giant, located about 139 light-years away, rotates so quickly that it completes one rotation every 2 days or less. The centrifugal force from this rapid spin causes the star to bulge dramatically at its equator. Measurements using interferometry, which combines light from multiple telescopes to achieve extremely high resolution, reveal that Achernar's equator is about 50% wider than the distance between its poles. If Achernar were a perfect sphere, it would look like a ball. As it actually exists, it resembles a somewhat squashed ellipsoid, noticeably wider than it is tall. This extreme flattening affects the star's appearance and physics. The poles are hotter and emit more light per unit area than the cooler, dimmer equatorial regions. If you could observe Achernar from different angles, it would appear brighter when viewed pole-on than when seen from the equator. Achernar demonstrates how rotation can fundamentally reshape a star, turning symmetry into distortion. Hypergiants are among the most unstable and short-lived stars in the universe, burning so intensely that they cannot hold themselves together. VY Canis Majoris, one of the largest known stars, loses mass through powerful stellar winds at a rate equivalent to Earth's entire mass roughly every year. This material, blown away by radiation pressure and convective turbulence, forms vast nebulae around the star. Over thousands of years, these winds can strip away a significant fraction of the star's total mass, enriching the surrounding space with heavy elements forged in the star's interior. The mass loss rate of hypergiants can be 100 to 1,000 times greater than that of ordinary red giants, making them prodigious sources of interstellar material. This shedding also affects the star's evolution, potentially determining whether it will explode as a supernova or collapse directly into a black hole. The nebulae around hypergiants glow with reflected starlight and emission from ionized gas, creating some of the most beautiful and complex structures visible through telescopes. These stars are cosmic fountains, pouring their substance back into the galaxy. Most stars emit light primarily in visible and infrared wavelengths, but the hottest stars radiate significant amounts of energy in the ultraviolet and even X-ray portions of the spectrum. The surfaces of O-type stars can exceed 40,000 degrees Celsius, hot enough that their peak emission shifts into the far ultraviolet. While the star's surface itself may not produce hard X-rays, the corona, the extremely hot outer atmosphere, can reach millions of degrees and emit X-rays. Additionally, certain exotic objects like accreting neutron stars and white dwarfs in binary systems produce intense X-ray emission, as material stolen from companion stars crashes onto their surfaces at tremendous velocities. The Sun itself emits X-rays from its corona, though not in large quantities. Space-based X-ray telescopes like Chandra and XMM Newton have revealed a universe ablaze with X-ray sources, from active stars to distant black holes. These high-energy photons carry information about the most extreme temperatures and energetic processes in the cosmos. Observing stars in X-rays reveals physics invisible in ordinary light, opening windows onto the universe's most violent phenomena. Stars are born from vast clouds of molecular hydrogen and dust known as molecular clouds or stellar nurseries. These regions can span hundreds of light years and contain enough material to create thousands or even millions of stars. Within these clouds, temperatures plunge to just a few degrees above absolute zero, creating conditions where hydrogen molecules can survive. Gravity slowly pulls denser clumps together, but the process is slow at first, resisted by gas pressure and magnetic fields threading through the cloud. Eventually, a clump becomes dense enough that its own gravity overwhelms the resistance, and it begins to collapse. As it does, it fragments into smaller pieces, each potentially becoming a star. The densest parts of these clouds appear dark in visible light because dust blocks starlight from behind, creating what astronomers call dark nebulae. But in infrared light, these regions glow with the heat of forming protostars, revealing the hidden process of stellar birth. Stellar nurseries are among the most active and dynamic regions in any galaxy, constantly transforming diffuse gas into concentrated points of light. The Orion Nebula, visible to the naked eye as the middle star in Orion's sword, is one of the nearest and most studied star-forming regions in our galaxy. Located about 1,344 light-years from Earth, it offers astronomers a nearby laboratory for understanding how stars and planetary systems form. The nebula glows pink and red in photographs, ionized by the intense ultraviolet radiation from a group of massive young stars at its heart called the Trapezium cluster. Within the nebula, thousands of stars are in various stages of formation, from protostars still gathering mass to newly formed stars just beginning their main sequence lives. The Hubble Space Telescope has captured stunning images of protoplanetary disks within the Orion Nebula, dark silhouettes against the bright background where planets are likely forming. What we see is just the surface. Deep within the densest parts of the cloud, hidden from optical view, even younger protostars are taking shape. The Orion Nebula is a cosmic maternity ward filled with the raw materials and newborn light of stellar creation. A sufficiently large molecular cloud can give birth to entire star clusters, with thousands or even tens of thousands of stars forming over a few million years. The process begins when something disturbs the cloud, perhaps the shockwave from a nearby supernova or the gravitational influence of a passing gas cloud. This disturbance triggers collapse in multiple regions simultaneously, creating numerous dense cores that each become a star. The stars don't form in isolation. They're born as siblings, often gravitationally bound together in open clusters. Over time, interactions between the young stars and the dispersal of leftover gas can cause the cluster to spread out, with some stars escaping into the galaxy while others remain loosely associated. The Pleiades, a beautiful open cluster visible to the naked eye, formed this way about 100 million years ago and still contains several hundred stars. Other clusters are denser and longer-lived, staying together for hundreds of millions of years. Each time we see a star cluster, we're looking at a stellar family, born together from the same cloud of gas. The journey from a collapsing cloud to a main sequence star is not instantaneous. For a Sun-like star, the entire process takes roughly 10 million years, though this varies depending on the star's mass. More massive stars form more quickly, sometimes in less than 1 million years, while the smallest red dwarfs might take 100 million years or longer. The process begins when a dense core in a molecular cloud starts to collapse under its own gravity. Over hundreds of thousands of years, the core contracts and heats up, becoming a protostar. The protostar continues to gather material from its surrounding disk, growing more massive. During this time, it's hidden within a cocoon of dust and gas, visible only in infrared light. Eventually, the protostar's core becomes hot and dense enough to ignite hydrogen fusion. At this moment, it becomes a true star, entering the main sequence. The powerful radiation and stellar wind from the newborn star blow away the remaining gas and dust, revealing the star to the universe. What remains is a stable, shining sun that will burn steadily for billions of years. One of the most striking features of forming stars is the jets they produce. These narrow streams of gas shoot outward from the star's north and south poles at speeds of hundreds of kilometers per second, sometimes extending for light years. The jets are powered by the same processes that allow the protostar to gather mass. As material from the surrounding disk spirals inward, it carries angular momentum that must be shed, and the jets are one mechanism for doing so. Magnetic fields threading through the disk channel some material outward along the rotation axis, accelerating it to high speeds. When these jets collide with surrounding gas, they create glowing shock waves called Herbig-Haro objects, some of the most beautiful structures in astronomy. The jets are temporary, lasting only as long as the star actively accretes material. Once the surrounding disk is depleted or blown away, the jets cease, and the star settles into its long main sequence life. These jets are the birth cries of stars, visible signatures of the violent processes that bring new suns into existence. The jets launched by young stars are not small-scale phenomena. Some extend for several light years, carving long tunnels through the molecular clouds from which they emerged. The HH212 jet, associated with a very young protostar, stretches about 1 light-year in each direction from the central star. The HH34 jet extends even farther, with visible structures spanning several light-years. As these jets plow into the surrounding gas at supersonic speeds, they create bow shocks and knots of emission where the jet material collides with stationary gas. The impacts heat the gas to thousands of degrees, causing it to glow in specific wavelengths that reveal its composition and velocity. Studying these jets helps astronomers understand how young stars shed angular momentum and how their energy affects the surrounding environment. The jets can also trigger further star formation by compressing nearby gas clouds. They are both disruptive and creative, simultaneously blowing apart their birth clouds and potentially seeding new generations of stars. These luminous outflows connect the smallest scales of star formation to the larger structure of star-forming regions. Surrounding most young stars is a flattened disk of gas and dust, the leftover material from the star's formation. Within these protoplanetary disks, the seeds of planetary systems take root. Dust grains, initially microscopic, stick together through electrostatic forces and gentle collisions, gradually building up into pebbles, then boulders, then kilometer-sized planetesimals. These planetesimals continue to collide and merge, sweeping up material in their orbits and growing into protoplanets. In the inner disk, where temperatures are higher, rocky planets like Earth form. Farther out, beyond what's called the frost line, water and other volatiles freeze into ice, allowing much larger planets to grow. These can become gas giants like Jupiter, massive enough to gravitationally capture hydrogen and helium from the surrounding disk. The entire process takes several million years, with planets forming while the star itself is still young. Modern telescopes have captured images of these disks, revealing gaps and spirals carved by forming planets, providing direct visual evidence of planetary birth. Every planetary system, including our own, began this way. The Sun and all the planets, moons, asteroids and comets in our solar system share a common origin. About 4.6 billion years ago, a portion of a molecular cloud began to collapse, possibly triggered by a nearby supernova. Most of the material fell into the center, becoming the Sun, while the remainder flattened into a rotating disk. Within that disk, dust grains collided and stuck together, eventually forming the terrestrial planets in the inner solar system and the gas giants farther out. The process wasn't entirely smooth. Planets migrated, their orbits shifting as they interacted gravitationally with each other and with the remaining disk material. Some planetesimals were flung into the outer solar system, becoming the Kuiper belt and Oort cloud, while others were ejected entirely. The final architecture we see today, with 4 rocky planets, 4 gas giants, and numerous smaller bodies, is the result of billions of years of gravitational sculpting. We know this history from studying meteorites, ancient rocks that formed in the earliest days of the solar system and have remained largely unchanged since. They are time capsules carrying the memory of our cosmic origins. While molecular clouds can slowly collapse under their own gravity, many star formation events are triggered by external forces. Shock waves from nearby supernovae can compress gas clouds, pushing them over the threshold where gravitational collapse begins. Similarly, collisions between galaxies create massive shockwaves that ripple through the gas, triggering intense bursts of star formation. In some regions, the powerful winds and radiation from massive young stars can compress adjacent gas, leading to sequential star formation, where one generation of stars triggers the birth of the next. These triggering events can explain why stars often form in groups rather than isolation. The shockwave doesn't just compress one small region, it affects a large volume of gas, creating multiple collapsing cores nearly simultaneously. This process has been ongoing throughout cosmic history. Many of the stars we see today, including possibly our own Sun, owe their existence to violent events that occurred millions or billions of years ago. Star formation is often a consequence of destruction, new light arising from the death of old stars. The Milky Way contains stars that formed very early in the universe's history, within just a few 100 million years of the Big Bang. These ancient stars, found primarily in the galaxy's halo and in globular clusters, are about 13.6 billion years old, only slightly younger than the universe itself, which is 13.8 billion years old. Astronomers identify these stars by their chemical composition. Early stars formed from gas containing almost no heavy elements, just hydrogen and helium with traces of lithium. As generations of stars lived and died, they enriched the galaxy with heavier elements, so younger stars like our Sun contain a much higher proportion of carbon, oxygen, iron, and other metals. By measuring the abundance of these elements in a star's spectrum, astronomers can estimate its age. The oldest stars are sometimes called population 3 stars if they have virtually no metals at all, or population 2 if they have small amounts. These ancient suns are witnesses to the early universe, survivors from an era when the first stars were just beginning to illuminate the cosmic dark. Every star, no matter how massive or luminous, eventually runs out of fuel. For main sequence stars, this means exhausting the hydrogen in their cores. When the hydrogen is gone, fusion slows or stops, and the star can no longer generate the outward pressure needed to counterbalance gravity. What happens next depends on the star's mass. Low-mass stars like red dwarfs can burn for trillions of years, but when they finally exhaust their fuel, they simply cool and fade. Medium-mass stars like the Sun expand into red giants, fusing helium and heavier elements in their cores before shedding their outer layers and becoming white dwarfs. Massive stars continue fusing heavier and heavier elements, building up layers like an onion until their cores fill with iron. Iron cannot release energy through fusion, so when the core becomes pure iron, the star's fate is sealed. Within seconds, the core collapses and the star explodes as a supernova. The death of a star is not merely an ending, but a transformation, a change from one state to another, each transition driven by the inexorable logic of physics. Stars with masses less than about 8 times that of the Sun follow a relatively gentle path to death. When such a star exhausts the hydrogen in its core, it expands into a red giant, fusing helium into carbon and oxygen. If the star is massive enough, it may briefly fuse carbon into heavier elements, but it never reaches the temperatures needed to fuse iron. Eventually, fusion ceases entirely, and the star's outer layers drift away into space, forming a planetary nebula. What remains is the exposed core, a white dwarf composed primarily of carbon and oxygen, compressed to incredible densities. White dwarfs no longer generate energy through fusion. They shine only with residual heat, gradually cooling over billions or trillions of years. Eventually, they will become black dwarfs, cold and dark, though the universe is not yet old enough for any black dwarfs to exist. White dwarfs represent the final resting state for the majority of stars in the universe. They are stellar fossils, the dense cores of once living suns, cooling silently in the darkness of space. Stars like our Sun, with masses between about 0.5 and 8 solar masses, undergo a dramatic transformation near the end of their lives. When the hydrogen in the core is exhausted, fusion moves to a shell surrounding the inert helium core. The energy released by this shell burning causes the star's outer layers to expand enormously, and the star becomes a red giant. Its surface cools to around 3,000 to 4,000 degrees, giving it a red hue, while its radius swells to tens or even hundreds of times its original size. Eventually, the core becomes hot enough to ignite helium fusion, producing carbon and oxygen. This phase is relatively brief, lasting only a few 100 million years. When the helium is exhausted, the star may undergo additional shell burning, but it cannot generate the temperatures needed to fuse carbon. The outer layers then puff away in a series of gentle expansions, forming a planetary nebula, while the core contracts into a white dwarf. The red giant phase is the prelude to death for most stars, a last brilliant expansion before the final fade. Our Sun is currently about halfway through its main sequence lifetime. In approximately 5 billion years, it will exhaust the hydrogen in its core and begin its transformation into a red giant. Over the next billion years or so, the Sun will grow steadily larger and brighter, increasing its radius by perhaps 200 times. Its outer layers will cool and take on a reddish color, while its total luminosity increases dramatically. The changes will be catastrophic for the inner planets. Earth's oceans will boil away long before the Sun reaches its maximum size, and eventually, Earth itself may be engulfed by the Sun's expanding atmosphere. Some models suggest Earth might survive at the edge of the Sun's photosphere, but it would be a scorched, lifeless rock. After spending a few 100 million years as a red giant, the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf about the size of Earth. That white dwarf will slowly cool over trillions of years, eventually fading to darkness. Our Sun's future is written in the physics of stellar evolution, inevitable and unchangeable. As the Sun swells into a red giant, its surface will extend outward, consuming Mercury and Venus entirely. The fate of Earth is less certain, but most models suggest it too will be engulfed. Even if Earth somehow survives at the outer edge of the Sun's atmosphere, conditions will be unbearable. Long before the Sun reaches its maximum size, Earth's surface temperature will rise to hundreds or thousands of degrees, the oceans will evaporate, the atmosphere will be stripped away, and the surface will melt into molten rock. By the time the Sun reaches its peak size, Earth will be at best a charred cinder orbiting within the Sun's tenuous outer layers, subjected to intense friction and heat. Eventually, the drag from the Sun's atmosphere will cause Earth's orbit to decay, and the planet will spiral inward, vaporizing as it plunges toward the Sun's core. If any trace of humanity survives that long, our descendants will have long since left Earth for distant stars. The Sun's red giant phase marks the inevitable end of our world, a reminder that even planetary homes are temporary. Stars with masses greater than about 8 times that of the Sun die spectacularly. After exhausting their hydrogen, these stars continue fusing heavier and heavier elements in their cores, working their way up the periodic table from helium to carbon to oxygen to silicon. This process continues until the core is filled with iron. iron is the end of the line because fusing iron consumes energy rather than releasing it. With no energy source to support the star against gravity, the iron core collapses catastrophically. In less than a second, the core implodes to a neutron star or black hole, and the outer layers rebound in a tremendous explosion called a supernova. For a few weeks, the supernova can outshine an entire galaxy, releasing as much energy in that brief time as the Sun will emit over its entire lifetime. The explosion scatters heavy elements into space, enriching the interstellar medium with the building blocks of planets and life. Supernovae are both endings and beginnings, violent deaths that seed the galaxy with the raw materials for future stars and worlds. At peak brightness, a supernova can reach absolute magnitudes of around -19 or -20, meaning it emits as much light as billions of normal stars combined. For a few weeks, a single exploding star can be brighter than all the hundreds of billions of stars in its host galaxy put together. From Earth, supernovae in distant galaxies appear as new points of light that suddenly flare up where no star was visible before, earning them the historical name new stars. If a supernova occurred within our galaxy at a distance of, say, a few thousand light years, it would be visible during the day and could cast shadows at night. The last supernova visible to the naked eye in the Milky Way was observed in 1604, known as Kepler's supernova. Astronomers eagerly await the next one, which is statistically overdue. The sheer energy output of a supernova is staggering, equivalent to all the energy the Sun will radiate over 10 billion years, released in just a few seconds. These explosions are among the brightest events in the universe, beacons of stellar death visible across vast cosmic distances. The elements heavier than hydrogen and helium that make up planets, life, and everything we see around us were forged in stars. Elements up to iron are created through fusion during a star's normal life, but elements heavier than iron require even more extreme conditions. These are produced during the supernova explosion itself, when the intense heat and neutron flux allow rapid neutron capture processes to occur. Gold, silver, platinum, uranium, and many other heavy elements are created in these final violent moments. When the star explodes, all of these elements, both those created during its life and those forged in the explosion, are blasted into space at speeds of thousands of kilometers per second. This material mixes with the interstellar medium, enriching it with metals. Future generations of stars that form from this enriched gas will have higher metal content, and planets that form around them will contain the rocky and metallic elements needed for terrestrial worlds and life. Every supernova is a cosmic furnace and a cosmic distributor, creating complexity and spreading it throughout the galaxy. For decades, supernovae were thought to be the sole source of elements heavier than iron. While they certainly contribute many of these elements, we now know the picture is more complex. In 2017, astronomers detected gravitational waves from two colliding neutron stars and observed the aftermath with telescopes. The light signature revealed the creation of heavy elements like gold, platinum, and uranium through a process called rapid neutron capture, or the R process. These kilonova events, as they're called, appear to be major, perhaps even dominant, sources of the heaviest elements in the universe. Additionally, lower mass stars in their asymptotic giant branch AGB phase produce many heavy elements through slow neutron capture, the S process, which occurs in their outer layers. These stars gently release their elements through stellar winds rather than explosions. The heavy elements in your body, the gold in jewelry, The platinum in catalytic converters all have origins in these diverse cosmic events, written in violence and patience across billions of years of galactic evolution. The explosion of a supernova blasts away the star's outer layers, but the core remains, compressed to extraordinary densities by the collapse that triggered the explosion. If the core's mass is between about 1.4 and 3 solar masses, it becomes a neutron star, a sphere of neutrons packed so densely that a teaspoon weighs 1 billion tons. If the core is more massive than about 3 solar masses, not even neutron degeneracy pressure can resist gravity's pull, and the core continues collapsing until it forms a black hole, a region of space-time where gravity is so strong that not even light can escape. The exact boundary between neutron star and black hole formation is still debated, as it depends on details of nuclear physics at extreme densities that we can't fully test in laboratories. Some massive stars might collapse directly to black holes without producing a visible supernova at all. These remnants, whether neutron stars or black holes, are the final monuments to massive stars, the densest and most extreme objects in the universe, carrying the memory of stellar death in their warped space-time. Despite their name, planetary nebulae have nothing to do with planets. They were named by early astronomers who, viewing them through small telescopes, thought they resembled the disks of planets. In reality, they are shells of gas ejected by stars like the Sun in their final stages of life. As a red giant sheds its outer layers, often in pulses, the expelled gas expands outward into space. When the hot core is finally exposed as a white dwarf, its intense ultraviolet radiation ionizes the surrounding gas, causing it to glow in beautiful colors. Different elements emit at specific wavelengths. Hydrogen glows red, oxygen green or blue, nitrogen red, creating the multicolored structures we see in images. Planetary nebulae come in a stunning variety of shapes, from simple spheres to complex bipolar structures with intricate details. They last only about 10,000 to 50,000 years before the gas disperses and becomes too thin to see, making them fleeting by cosmic standards. These glowing shells are the tombstones of sun-like stars, marking their passage from life to death. A planetary nebula is a temporary phenomenon, beautiful but brief. When a star first sheds its outer layers, the gas is dense enough, and the white dwarf hot enough that the nebula glows brightly. Over time, the gas continues to expand and thin out, while the white dwarf cools and its radiation weakens. After roughly 10,000 to 50,000 years, the nebula has expanded so much that it becomes too diffuse to emit visible light, and it fades into the general interstellar medium. The white dwarf at the center continues cooling for billions of years, but the nebula itself is gone, dispersed and mixed with other gas in the galaxy. Some of that material will eventually be incorporated into new stars and planets, continuing the cycle of stellar birth and death. In cosmic terms, planetary nebulae are ephemeral, visible for only a brief window in the death of a star. Astronomers have catalogued thousands of them in our galaxy, each representing a star in that fleeting transition between giant and white dwarf, offering a preview of the Sun's fate billions of years hence. The Ring Nebula, also known as Messier 57 or M57, is one of the best-known planetary nebulae and a favourite target for amateur astronomers. Located about 2,300 light-years away in the constellation Lyra, it appears as a small smoke ring-like structure in small telescopes. The nebula formed about 1,600 years ago when a sun-like star exhausted its fuel and shed its outer layers. From Earth, we see the nebula almost perfectly edge-on, looking down the axis of a barrel-shaped shell of gas. The ring appearance is an illusion of perspective. We're actually looking at a three-dimensional bubble with thicker walls. At the center sits a white dwarf, the exposed core of the original star, with a surface temperature of about 120,000 degrees Celsius. This intense heat ionizes the surrounding gas, causing it to glow. Images from the Hubble Space Telescope reveal intricate details in the Ring Nebula's structure, including knots of denser material and faint outer halos from earlier mass loss. The Ring Nebula is a snapshot of stellar death, frozen in time for us to study. Once a white dwarf forms, it has no source of energy generation. It shines only with leftover thermal energy from its past life. Over time, it radiates this heat away into space and gradually cools. The cooling process is extraordinarily slow. A white dwarf might start with a surface temperature of 100,000 degrees or more, glowing brilliant white or even blue. Over billions of years, it cools to tens of thousands of degrees, then thousands, changing from white to yellow to red, and eventually fading beyond visibility. Theoretical calculations suggest it would take trillions of years for a white dwarf to cool completely to near absolute zero, becoming a black dwarf, a cold, dark sphere of crystallized carbon and oxygen. The universe is only 13.8 billion years old, which means no white dwarf has yet had time to become a black dwarf. Every white dwarf that has ever formed still glows at least faintly. They are cooling embers scattered throughout the galaxy, marking the graves of billions of sun-like stars, slowly fading but not yet extinguished. The final fate of a white dwarf, after all its heat has radiated away, is to become a black dwarf, a cold, dark object no longer emitting significant light. But this stage is entirely theoretical because the cooling time is so immense. The oldest white dwarfs in our galaxy, formed from the first generation of sun-like stars billions of years ago, are still warm enough to glow faintly. Calculations suggest that even the oldest white dwarfs still have surface temperatures of several thousand degrees. To cool to near absolute zero would take not billions but trillions of years, far longer than the current age of the universe. In fact, the universe would need to be perhaps 100 times older than it is now before the first black dwarfs appear. This means that black dwarfs are objects of the far future, relics of a much older, colder cosmos. They belong to an era when star formation has ceased, when galaxies have dimmed, and when the universe enters its long, slow decline toward darkness. For now, every stellar remnant in the sky still carries some whisper of heat from its luminous past. When two stars are gravitationally bound, they don't orbit each other in the way a moon orbits a planet. Instead, both stars orbit a point between them called the barycenter or center of mass. If the stars have equal mass, the barycenter sits halfway between them. If one star is more massive, the barycenter lies closer to the heavier star, and in extreme cases where one star is far more massive, the smaller star appears to orbit the larger one, but technically both are orbiting their common center. The period of the orbit depends on the star's masses and their separation. Close binaries can complete an orbit in hours or days, while wide binaries might take thousands of years. By carefully measuring the orbits, astronomers can determine the star's masses using Kepler's laws, making binary stars invaluable for understanding stellar properties. The gravitational dance of binary stars is one of the most fundamental motions in the universe, a cosmic choreography governed by Newton's and Einstein's laws, playing out across every scale from light hours to light years apart. In close binary systems, The two stars can be so near each other that their outer atmospheres touch or overlap. When one star evolves and expands into a giant, its outer layers can spill over onto its companion in a process called mass transfer. Material flows from the donor star through a point called the Lagrange point, where the gravitational pulls of the two stars balance, and spirals onto the companion, often forming an accretion disk. This mass transfer can dramatically alter both stars' evolution. The donor star loses mass and may be stripped down to its core, while the receiving star gains mass and may spin up or change its structure. In some cases, the interaction can trigger nova explosions or even lead to the stars merging. These interacting binaries are responsible for some of the most spectacular phenomena in astronomy, from X-ray binaries powered by neutron stars to type Ia supernovae from white dwarfs that accumulate too much mass. Close binaries remind us that stellar evolution is not always a solitary affair. The nearest star system to our Sun, Alpha Centauri, is actually a family of 3 stars orbiting each other. Alpha Centauri A and B are similar to the Sun, with masses of about 1.1 and 0.9 solar masses respectively, and they orbit each other every 80 years at a distance that varies from about 11 to 36 astronomical units. Much farther out, about 13,000 astronomical units away, orbits Proxima Centauri, a small red dwarf that takes over 500,000 years to complete one orbit around the central pair. Proxima is actually the closest star to the Sun at 4.24 light-years, slightly closer than Alpha Centauri A and B at 4.37 light-years. This triple system offers a fascinating laboratory for studying stellar interactions and planet formation. In recent years, planets have been discovered around both Proxima Centauri and Alpha Centauri A, raising the tantalizing possibility that our nearest stellar neighbors might host worlds capable of supporting life. Alpha Centauri has long been a target for future interstellar missions, the first stars humanity might hope to visit. Sirius, the star that outshines all others in Earth's night sky, is not alone. It has a faint companion called Sirius B, a white dwarf that orbits the bright primary star every 50 years. Sirius A, the visible star, is about twice the mass of the Sun and 25 times more luminous, while Sirius B is a dense stellar remnant about the size of Earth but containing roughly the mass of the Sun. The white dwarf was once the more massive of the two stars, but it exhausted its fuel and collapsed into its current state millions of years ago. When it was a giant, it may have been brighter than Sirius A is today. The binary nature of Sirius was first suspected in the 19th century when astronomers noticed that Sirius A wobbled slightly in its path across the sky. The companion was finally observed directly in 1862, confirming the prediction. Sirius B is now one of the nearest white dwarfs to Earth, offering astronomers a valuable opportunity to study these exotic stellar remnants up close. Together, the Sirius system demonstrates the diversity hidden within even the most familiar stars. Sirius B is a fascinating object in its own right. Though it appears very faint next to the brilliant Sirius A, it's actually quite hot, with a surface temperature around 25,000 degrees Celsius, hotter than the Sun. Its faintness comes from its tiny size, roughly the diameter of Earth, which gives it very little surface area from which to radiate light. The density of Sirius B is astonishing, about 1,000,000 times that of water, meaning a sugar cube-sized piece would weigh as much as a car. This white dwarf was likely born about 120 million years ago, when its progenitor star, originally more massive than Sirius A, exhausted its fuel and shed its outer layers. The system's history is written in its current configuration. At the time, Sirius B was a giant. It may have transferred some mass to Sirius A, explaining why Sirius A rotates unusually fast. Now, Sirius B cools quietly, shining with residual heat, a monument to its past life and a preview of the future awaiting Sirius A billions of years from now. In binary systems where the orbital plane is aligned nearly edge-on from Earth's perspective, one star periodically passes in front of the other, blocking some of its light. These are called eclipsing binaries, and they produce characteristic dips in brightness that repeat with every orbit. When the larger or brighter star is eclipsed, the system dims significantly. When the smaller or dimmer star passes behind, the dip is less pronounced. By measuring the timing, depth, and duration of these eclipses, astronomers can determine the star's sizes, masses, temperatures, and orbital properties with remarkable precision. Eclipsing binaries are crucial for calibrating our understanding of stellar physics because they provide direct geometric measurements rather than relying on models. Some eclipsing binaries have orbital periods of just hours, while others take years. The eclipses are perfectly regular, predictable with extraordinary accuracy, making these systems natural laboratories for testing theories of stellar structure and evolution. They're proof that sometimes, to understand stars better, we simply need to watch them carefully as they pass in front of one another. Algol, located in the constellation Perseus, is one of the best-known variable stars and has been observed for thousands of years. The ancient Egyptians may have noted its variability, and Arabic astronomers named it the demon star for its peculiar behavior. Algol consists of a bright blue-white star eclipsed every 2.87 days by a dimmer, cooler companion. During the eclipse, Algol's brightness drops by about 70%, a change easily visible to the naked eye. For most of its cycle, Algol shines at magnitude 2.1, but during the eclipse, it dims to magnitude 3.4, remaining dimmed for about 10 hours. The system actually contains 3 stars, with a third more distant member orbiting the close pair. Algol's eclipses are so regular that they can be predicted centuries in advance. Observing Algol was one of the first proofs that stars could be variable, and that some of that variation resulted from geometry rather than changes in the stars themselves. It remains a favorite target for amateur astronomers learning about eclipsing binaries. In the most extreme close binaries, called contact binaries, the 2 stars are so close that they touch, sharing a common outer atmosphere. These systems resemble peanuts, with 2 stellar cores embedded in a single elongated envelope of gas. Contact binaries typically consist of lower mass stars, often similar in size, orbiting each other in periods of less than a day. Material flows between the stars continuously, and the entire system rotates as if it were nearly a single object. The physics of contact binaries is complex because the shared envelope affects both stars' evolution in ways that are difficult to model. Over time, these systems may merge completely, forming a single, rapidly rotating star. Observations suggest that contact binaries are more common than once thought, perhaps making up a significant fraction of all binary systems. They represent an extreme stage of binary evolution, systems that have drifted too close together and lost their individual identities. To observe one is to see 2 stars in the process of becoming one, a cosmic merger playing out over millions of years. While many triple-star systems have stable hierarchical configurations where a close binary is orbited by a distant third star, others are more chaotic. In systems where all three stars have comparable separations and masses, the gravitational interactions become complex and can lead to unpredictable behavior. Stars may exchange partners, swap orbits, or even eject one member of the system entirely. Simulations show that some triple systems are inherently unstable and will eventually decay, leaving a close binary and a single star flung outward at high speed. Other triple systems exhibit resonances and precessions that make their long-term evolution difficult to predict. These systems are natural laboratories for studying three-body gravitational dynamics, one of the classic problems in physics that has no general analytical solution. The orbits must be calculated numerically, and even small changes in initial conditions can lead to wildly different outcomes. Chaotic triple star systems remind us that the universe is not always orderly, and that even the motions of stars can be subject to unpredictability and chance. Planets don't only orbit single stars. In binary systems, planets can exist in two configurations: circumbinary orbits, where the planet orbits both stars, and S-type orbits, where the planet orbits just one star while the other remains more distant. Circumbinary planets, sometimes called Tatooine planets, after the fictional world in Star Wars, have been discovered around several close binary systems. These planets must orbit far enough from the binary that the gravitational influence of both stars provides a stable, nearly circular combined potential. Closer in, the competing pulls of the two stars would destabilize planetary orbits. For an observer on such a planet, the sky would feature two suns, sometimes setting together, sometimes separately, creating complex patterns of light and shadow. The habitability of circumbinary planets depends on many factors, including the star's properties and the planet's orbit, but there's no fundamental reason they couldn't support life. These worlds expand the possibilities of where and how planets form, showing that even in the complex dynamics of binary stars, stable planetary systems can exist. Our home galaxy, the Milky Way, is a vast spiral structure containing an estimated 100 to 400 billion stars. The uncertainty in this number comes from the difficulty of counting stars we cannot see. Many stars are too faint or too obscured by dust to detect, especially in the dense central bulge and disk. Most of these stars are red dwarfs, small and dim, while massive luminous stars are rare but highly visible. The Milky Way's stars are not uniformly distributed. They're concentrated in a thin disk with prominent spiral arms, with a dense bulge at the center, and a sparse halo of old stars surrounding the whole structure. Our Sun sits about 26,000 light-years from the galactic center, roughly halfway out in the disk. From our perspective, we see the galaxy edge on as a band of light across the night sky, the combined glow of millions of unresolved stars. Every star we see individually with the naked eye is part of the Milky Way, members of our stellar neighborhood scattered across a structure 100,000 light-years wide. The Milky Way's structure includes several components: a thin disk, a thick disk, a central bulge, and a diffuse halo. The majority of stars, perhaps 85 to 90%, reside in the thin disk, a flattened structure only about 1,000 light-years thick but 100,000 light-years in diameter. This is where active star formation occurs, where gas and dust concentrate, and where the beautiful spiral arms trace patterns of ongoing stellar birth. The thick disk, lying above and below the thin disk, contains older stars with less organized orbits. The central bulge is a dense, roughly spherical concentration of old stars, while the halo contains ancient globular clusters and scattered individual stars, remnants from the galaxy's early formation. This distribution reflects the Milky Way's history, with the oldest stars in the halo and bulge dating back nearly to the galaxy's formation, while the disk continues to form new stars even today. The Sun's location in the disk places us in a region of moderate density, not too crowded, not too empty, orbiting steadily in the flow of galactic rotation. The Sun, along with all the planets and everything in our solar system, is in constant motion, orbiting the center of the Milky Way. This journey takes approximately 225 to 250 million years, a period sometimes called a galactic year or cosmic year. Since the Sun formed about 4.6 billion years ago, it has completed roughly 20 orbits around the galaxy. The last time the Sun was in its current position in the galaxy, dinosaurs roamed the Earth. 1 galactic year from now, if the Sun still exists, Earth will be vastly different or perhaps gone entirely. This motion places our cosmic address in perspective. We're not just on a planet orbiting a star, but on a star orbiting the center of a galaxy, which itself is moving through intergalactic space. The Sun's orbital path is not perfectly circular, but slightly elliptical, and it bobs up and down through the galactic plane over time. Every 30 million years or so, we cross through the densest part of the disk, potentially encountering more dust, gas, and gravitational perturbations from nearby stars. The Sun's motion around the galactic center is far from leisurely. It travels at approximately 230 kilometers per second, or about 828,000 kilometers per hour. At this speed, the Sun could circle Earth's equator in about 6 minutes. Yet, despite this tremendous velocity, the distances are so vast that one orbit takes 250 million years. The Sun's motion is not just around the galaxy, it also moves up and down through the galactic plane, oscillating like a wave with a period of about 60 million years. Additionally, the Sun has its own peculiar motion relative to neighboring stars, moving at about 20 kilometers per second toward the constellation Hercules. When you add all these motions together, our solar system is on a complex, spiraling path through the galaxy. Every second, we travel thousands of kilometers through space, yet from our perspective, the stars appear fixed, their positions changing only over centuries or millennia. The scale of the galaxy makes even rapid motion seem imperceptibly slow. Globular clusters are among the most spectacular objects in the galaxy. Dense spherical collections of stars that can contain anywhere from tens of thousands to millions of members. These clusters orbit in the Milky Way's halo, high above and below the galactic disk. The stars within them are tightly packed, especially toward the center where stellar densities can be thousands of times higher than in the Sun's neighborhood. In the core of a globular cluster, stars may be separated by only a few light weeks, close enough that their gravitational interactions are frequent. Most globular cluster stars are old, 10 to 13 billion years, dating back to when the Milky Way was young. They formed in a single burst of star formation and have been bound together ever since. Because they're so old, globular clusters contain no massive luminous stars, those burned out billions of years ago. What remains are long-lived red dwarfs, evolved red giants, and white dwarfs. Studying globular clusters helps astronomers understand the early history of the galaxy. Omega Centauri, visible to the naked eye from the southern hemisphere, is the most massive globular cluster associated with the Milky Way. It contains an estimated 10 million stars and has a mass equivalent to about 4 million solar masses. Located roughly 16,000 light-years away, it appears as a large, fuzzy patch of light, brighter than most stars in the sky. Omega Centauri is unusual for a globular cluster, because its stars show a range of ages and chemical compositions, suggesting it may have had a more complex formation history than typical clusters. Some astronomers believe it might be the core of a dwarf galaxy that was stripped of its outer stars when it merged with the Milky Way billions of years ago. Observing Omega Centauri through a telescope reveals a breathtaking sight, thousands of stars packed into a glowing sphere, their combined light creating a luminous ball. Standing on a planet within Omega Centauri, the night sky would be dazzling, filled with thousands of stars brighter than Venus appears from Earth. Occasionally, stars are accelerated to such high velocities that they escape their host galaxies entirely, becoming intergalactic wanderers. These hypervelocity stars can travel at speeds exceeding 1,000 kilometers per second, far faster than the escape velocity from the Milky Way. Several mechanisms can create hypervelocity stars. A common one involves a close encounter with the supermassive black hole at the galaxy's center, where a binary star system is torn apart, with one star captured and the other flung outward at tremendous speed. Another mechanism involves the gravitational slingshot effect during galaxy mergers, where stars from one galaxy can be ejected by the other's black hole. Dozens of hypervelocity stars have been discovered fleeing the Milky Way, tracing long arcs into intergalactic space. Most will never return, condemned to spend billions of years traveling alone through the void between galaxies. These stellar exiles are reminders that galaxies are dynamic, violent places where even something as massive as a star can be cast adrift by forces beyond its control. Hypervelocity stars are among the fastest objects in the galaxy, moving at speeds that dwarf the typical orbital velocities of stars around the galactic center. Some have been clocked at over 1,200 kilometers per second, more than 5 times the speed needed to escape the Milky Way's gravitational pull. At these velocities, they will leave the galaxy within tens of millions of years, journeying into the emptiness of intergalactic space. The discovery of hypervelocity stars was unexpected and has opened new windows into galactic dynamics. Their trajectories can be traced backward to find their origins, often pointing toward the galactic center and its supermassive black hole. The fastest hypervelocity stars may even escape the local group of galaxies entirely, traveling hundreds of millions of years before potentially joining another galaxy cluster or remaining forever isolated. For any planets orbiting such a star, the journey would be extraordinary, watching the Milky Way shrink behind them while the void of intergalactic space stretches ahead, a cosmic exile lasting billions of years. Not all stars belong to galaxies. In the vast spaces between galaxies, there exist rogue stars, drifting alone through intergalactic space. Some are hypervelocity stars ejected from their home galaxies, while others may have been torn away during galaxy mergers and interactions. Observations of galaxy clusters reveal diffuse light between galaxies, produced by these scattered intergalactic stars. In some clusters, up to 50% of the total stellar mass may lie in intergalactic space rather than within individual galaxies. These stars are incredibly isolated. The nearest neighboring star to an intergalactic sun might be millions of light years away. If planets orbit such a star, their night sky would be profoundly dark, with only the faint distant glow of galaxies visible, like islands of light in an endless ocean of darkness. Intergalactic stars are the ultimate cosmic wanderers, separated from any stellar community, traveling through the void for billions of years. They remind us that space between galaxies, though often called empty, is punctuated by solitary lights, cast adrift by the violent dynamics of galactic evolution. While galaxies like the Milky Way form stars at a steady, moderate pace, some galaxies undergo episodes of furious star formation called starbursts. During these events, stars are born at rates 100 to 1,000 times higher than normal, consuming vast amounts of gas in just a few million years. Starburst galaxies glow intensely in infrared light, heated by the radiation of countless young, massive stars hidden within dense clouds of dust. These bursts are often triggered by galaxy collisions or mergers, where gravitational interactions compress gas clouds and ignite waves of star formation. The antennae galaxies, a pair of colliding spirals, is a famous example, with regions of intense starburst visible in telescope images. Starbursts are brief by cosmic standards, lasting perhaps 10 to 100 million years before the available gas is exhausted or blown away by supernova and stellar winds. Afterward, the galaxy settles into a quieter state, enriched with heavy elements from the short-lived massive stars. Starburst galaxies show us that star formation is not always gradual, but can occur in dramatic, explosive episodes. Sirius has held humanity's attention for millennia, dominating the winter sky in the northern hemisphere and visible year-round from much of the southern hemisphere. Its brightness, magnitude -1.46, makes it nearly twice as bright as the next brightest star, Canopus. Part of Sirius's brilliance comes from its intrinsic luminosity, about 25 times that of the Sun, but its apparent brightness is also aided by its proximity at just 8.6 light-years away. Ancient Egyptians associated Sirius with the goddess Isis and used its heliacal rising, its first appearance in the dawn sky after a period of invisibility, to predict the annual flooding of the Nile. The Greeks and Romans also noted Sirius, calling it the dog star, because it's the brightest star in the constellation Canis Major, the Greater Dog. Modern astronomy has revealed Sirius to be a binary system with a white dwarf companion, but to the naked eye, it appears as a single dazzling point of light, a beacon that has guided and inspired observers for thousands of years. Polaris holds a special place in human history and navigation because it sits almost directly above Earth's North Pole, making it appear nearly stationary in the sky while other stars rotate around it. But Polaris is far from ordinary. It's actually a supergiant star about 2,500 times more luminous than the Sun and roughly 50 times larger, located approximately 430 light-years away. If Polaris were at the same distance as Sirius, it would shine far brighter, dominating the night sky. Polaris is also a multiple star system, with two smaller companions orbiting the main star. Additionally, Polaris is a Cepheid variable, pulsating slightly with a period of about 4 days, though the variations are small and not noticeable to the naked eye. Its position as the North Star is temporary, a consequence of Earth's axial precession. In about 13,000 years, the bright star Vega will take over the role. For now, Polaris remains our guide, a brilliant supergiant masquerading as a modest beacon in the northern sky. Betelgeuse is one of the most closely watched stars in the sky because it's nearing the end of its life and could explode as a supernova at any time. When will this happen? Astronomical timescales make predictions difficult. It could be tomorrow, or it could be 100,000 years from now. Either way, in cosmic terms, that's essentially soon. When Betelgeuse does explode, it will be spectacular. At its distance of about 550 light-years, the supernova will likely reach a peak brightness rivaling the full moon, visible even during daylight. It will remain bright for weeks or months before fading. The explosion will not harm Earth, we're far too distant for that, but it will provide an unprecedented opportunity to study a supernova up close. Betelgeuse has already shown unusual behaviour, dimming significantly in 2019 to 2020, sparking speculation that the supernova might be imminent. The dimming turned out to be caused by a massive cloud of dust ejected by the star, but it reminded astronomers that Betelgeuse is volatile and unpredictable, a giant on the brink of its final brilliant end. Proxima Centauri, a small red dwarf in the Alpha Centauri system, holds the distinction of being the Sun's nearest stellar neighbour. At a distance of just 4.24 light-years, or about 40 trillion kilometres, it's the closest star beyond our solar system. Despite this proximity, Proxima is too faint to see with the naked eye, requiring a telescope for observation. It's a typical red dwarf, with about 12% the mass of the Sun and less than 0.2% of its luminosity. Proxima gained even more attention in 2016 when astronomers discovered Proxima Centauri b, an Earth-sized planet orbiting in the star's habitable zone. The possibility of a potentially habitable world so close has made Proxima a prime target for future interstellar missions. The Breakthrough Starshot initiative, for example, proposes sending tiny spacecraft to Proxima Centauri at 20% the speed of light, reaching it in about 20 years. For now, Proxima remains our closest stellar companion, a faint red ember holding the tantalizing possibility of nearby worlds. Barnard's star, a red dwarf located 6 light-years away, is notable for having the highest proper motion of any star in the sky. Proper motion refers to a star's apparent movement across the celestial sphere over time, caused by its actual motion through space relative to the Sun. Barnard's star moves at 10.3 arc-seconds per year, fast enough that it shifts its position against background stars noticeably over just a few years. In about 10,000 years, it will have moved a distance equal to the width of the full moon. This rapid motion is partly due to Barnard's star's high velocity relative to the Sun, about 140 kilometers per second, and partly due to its proximity. Barnard's star is approaching us and will make its closest pass in about 9,800 years, when it will be just 3.75 light-years away, briefly becoming our second closest stellar neighbour after Proxima Centauri. Its rapid motion makes it a valuable target for studying stellar kinematics and understanding the dynamics of our local stellar neighbourhood. VY Canis Majoris, a red hypergiant located about 3,800 light-years away, was long considered one of the largest stars in the galaxy. Early estimates suggested a radius over 2,000 times that of the Sun, large enough to engulf Saturn's orbit. However, more recent measurements using advanced techniques have revised this downward to about 1,420 solar radii. Still enormous, but not quite the record holder. The difficulty in measuring such stars comes from their diffuse, irregular outer atmospheres, which make defining an exact edge challenging. VY Canis. Majoris is surrounded by a vast, complex nebula of material it has ejected, making observations even more complicated. Despite no longer holding the title of largest star, VY Canis Majoris remains one of the most luminous stars known, shining with the power of about 270,000 suns. It's highly unstable and will likely explode as a supernova within the next 100,000 years, leaving behind either a neutron star or a black hole. Rigel, the brightest star in the constellation Orion, is a blue supergiant located about 860 light-years away. Despite being more distant than Betelgeuse, Rigel appears slightly brighter from Earth because of its tremendous luminosity, roughly 120,000 times that of the Sun. With a surface temperature around 11,000 degrees Celsius, Rigel glows intense blue-white, pouring out most of its energy in the ultraviolet. If Rigel replaced the Sun, Earth would be instantly vaporized by the intense radiation. Rigel is also a multiple star system, with at least 3 or 4 companion stars orbiting the bright primary. Like most blue supergiants, Rigel is relatively young, perhaps only 8 to 10 million years old, and it will end its life in a supernova explosion within the next million years or so. Its name comes from the Arabic Ra'il Jawza, meaning the foot of Jawza, referring to its position marking Orion's foot. Rigel is one of the most luminous stars visible to the naked eye, a brilliant beacon of the winter sky. Antares, whose name means rival of Mars in Greek, is a red supergiant in the constellation Scorpius. With a radius about 700 times that of the Sun, Antares would extend past the orbit of Mars if placed at the centre of our solar system. Like other red supergiants, Antares has a relatively cool surface, around 3,500 degrees Celsius, giving it a deep red colour that rivals the planet Mars, hence its name. Despite this coolness, its enormous size makes it extremely luminous, about 75,000 to 90,000 times more luminous than the Sun. Antares is surrounded by a faint nebula of material it has shed through strong stellar winds, and it has a hot blue companion star, Antares B, orbiting it every 1,200 years or so. The primary star is nearing the end of its life and will explode as a supernova, possibly within the next million years. When it does, it may briefly outshine every other star in the night sky. For now, Antares glows red and fierce, the heart of the Scorpion, a reminder of stellar grandeur. After Sirius, the second brightest star in Earth's night sky is Canopus, a white supergiant in the constellation Carina. Located about 310 light-years away, Canopus shines with an intrinsic luminosity roughly 15,000 times that of the Sun. Its great distance means that despite its brilliance, it appears much dimmer than it would if it were as close as Sirius. Canopus is named after the navigator of King Menelaus in Greek mythology and has been an important star for navigation in the Southern Hemisphere for centuries. It's visible from most of the Southern Hemisphere year-round and from southern latitudes in the Northern Hemisphere during winter. Canopus is also one of the brightest stars in absolute terms, meaning if all stars were placed at the same distance, Canopus would be among the most luminous visible to the naked eye. Its spectral type, F0, places it as a white supergiant with a surface temperature around 7,000 to 8,000 degrees Celsius, hotter than the Sun but cooler than blue giants like Rigel. Deneb, marking the tail of Cygnus the Swan, is one of the most intrinsically luminous stars visible without a telescope. Located between 1,500 and 2,600 light-years away, the uncertainty comes from difficulty in measuring precise distances to such remote objects. Deneb shines with a luminosity estimated at 200,000 times that of the Sun, making it one of the most powerful stars in our region of the galaxy. Despite its great distance, Deneb appears as a bright first magnitude star, one of the vertices of the summer triangle asterism. If Deneb were at the same distance as Sirius, it would shine as brightly as a crescent moon and cast visible shadows at night. Deneb is a blue-white supergiant with a surface temperature around 8,500 degrees Celsius. Like other supergiants, it's nearing the end of its life and will eventually explode as a supernova. When it does, it may briefly become one of the brightest objects in the sky, visible even in daylight. Deneb's remote brilliance reminds us that the brightest stars in our sky are not always the closest, but sometimes the most intrinsically powerful. And so we come to the end of our journey through 100 quiet truths about stars. We've travelled from the smallest red dwarfs to the largest hypergiants, watched stars be born in vast nebulae and die in gentle planetary nebulae or violent supernovae. For now, there's nothing more you need to do. Just allow yourself to sink deeper into rest. Let your breath become slow and even, and feel the weight of the day dissolve into darkness. Sleep peacefully, dream deeply, and know that the same starlight filling the night sky flows through you as well. Good night.